Welcome back to Bio 6612. In week 9, we're going to cover count data and Poisson regression. So often in biomedical studies, the response variable y is a count. And in this case, the observed data, each record is a cell, and for the response, the event count. The response is the event count in each cell. I'll go through several examples in this lecture, but just below I have a couple listed, and that can include the number of incident lung cancer cases in a particular state or region, or the number of acute liver failure cases diagnosed between particular dates among, say, males of a particular age working in a particular region, or the number of physician visits for influenza among college students in 2005. A specific example of count response data is given below, and this is a table from the Dobson book on page 169. And these are deaths from coronary heart disease after 10 years among British doctors. When I said the count in a cell, I'm talking about cells of a table here. In this case, the outcome is a count variable number of deaths. These counts are given in this part of the table. And each of these rows, the counts in each of these rows is one cell. So this cell, the number of deaths would be 32. And some covariates you might be interested in would be smoking status, whether or not the counts in this table are for smokers or non-smokers, and then the age group of people who fall into this table. We also have this variable person years, and that's the number of person years of exposure for those in this particular cell of the table. Then that sort of introduces the concepts of counts versus rates. So in the previous example, we had different numbers of person years for each cell in the table. If this follow-up time, in that case person years, but it can be other things, this is called the follow-up time or exposure. If this is constant across all subjects or cells, in the previous example it was not, but if it is constant across all subjects or cells, we can model the mean count directly, in which case we are modeling the expected value of y, which is a count, given the set of covariates, through some inverse link function of the covariates and the expected and the weights, the betas. If we don't have constant exposure across all subjects or cells, then we will model the rate, which is the expected count divided by the exposure time. So yeah, rates are typically reported as events per unit of time or per unit of person time. And that unit of time, the units in that time variable don't matter, but they have to be the same for each, same units for each cell. So here's another example. This is asthma and air temperature. In this example, a group of clinicians wishes to study the association between air temperature and physician claims for asthma. So the outcome is the number of physician claims for asthma, and we're interested in how air temperature affects the number of claims. In this case, we have 16 claims for an average air temperature of 51 in the month of September. And in this example, the exposure time is per month. So each month we have the average temperature and number of claims. So I took that data and I fit a linear regression model to the data. And this might not be an appropriate model for count data linear regression, but later in the lecture we'll fit a more appropriate model. So if you want to load that data into R, you can use this code chunk here. This will just define a data frame with the data in the previous table. You can model it using a linear model using this line of code, where we're modeling the outcome, which is number of asthma claims against the average air temperature. And we'll see here that relationship is not significant. Some plots from that linear regression model are shown here. On the left-hand side, you have the points of the data plotted, the number of asthma claims against the average temperature, and the blue line is the regression line, the linear regression line fit through the data. And from this fit, we see that the number of asthma claims, average number of asthma claims is lower for higher air temperatures. However, it's not really a great fit through the data. And one of the reasons that you can see from looking at the residuals plot, where the residuals aren't really randomly scattered around zero, you tend to have more variance in the residuals at lower air temperatures. So we might want to consider a different fit, which we'll do in the next lecture. Another example of count data comes from this fertility data set. And in this data comes from a 1985 study of German women aged 44 or older and in first marriages at the time of the study. And we're interested in the number of children per woman based on the set of explanatory variables given below. So the outcome is children, the number of children per woman, and we have several variables. This data comes from the counter package in R, and you can load it into your console by installing that counter library and then loading the data with this line of code here. So I said that linear regression might not be appropriate for count data, and so we can actually use Poisson regression instead. The Poisson model is the most frequently used model for count data. And the general setup for this model is I indexes subjects or cells, yi is the event count for the ith subject or cell, xi is the covariate vector for that subject or cell, and ti is the exposure for that subject or cell. And we'll get into examples of modeling this data as well as deriving the model in the next set of lectures.